All right, guys, so what we're going to be looking at here is we're going to be looking at different types of series. Now, the series that we're going to be looking at here are a little bit different than like the Taylor series that you're accustomed to seeing, or even the power series. These are just series that we look at before we introduce the variables, but they do appear on the AP exam, so we need to look at each of the different types. So let's just kind of jump in and take a look at what we need to here. The first thing that we need to ask ourselves is, what is an infinite series? Now, an infinite series is just a whole bunch of terms, and they're being added together, that when we notice each of the individual terms, we have one number, then another number, then another number written after that, they have a pattern, and that pattern is going to continue on forever. Most of the time in a series, we are given what is called the general term, which just means if I wanted to know, if I didn't want to write them in order, where the first, the second, the third, the fourth, the fifth, the sixth term, if I just wanted to write like the 52nd term or the 403rd term, then I would just plug that particular number into the general term, which is what we usually have. So like, usually we have a summation. It goes from n equals some number, sometimes one, sometimes something else, to infinity. And then we have that general term that we have, like I've got written right there, that just means that we're going to plug a number in for n, and whatever number it is, that's the particular term as we go along the series as we're adding all of those numbers up. Now, one thing that is very important to us when it comes to series is we want to know whether a series is going to be convergent or divergent. When we have an infinite series and we say that it's convergent, what is happening is that series is actually adding up to a particular number. Like it might not look like it, it might not seem like it because you're always adding numbers to a series, but it is possible that we can tell whether or not a number is convergent, that it adds up to a specific number. Most of the time when we look at these, we won't know what that number is that they add up to, but you can determine whether or not it's actually going to add up to a specific number. If a series is divergent, then we just say, you know what, those terms are not going to add up to a specific number. That's just going to keep getting bigger and bigger and bigger, and there's no way to tell exactly what it's going to add up to. Now, we did talk about a bunch of series. We're going to go over all of these here in just a minute, but we have all of these series that we are going to talk about, as well as tests that we can use to determine whether or not those series are going to be convergent or divergent. So the first type of series we're going to talk about is a geometric series. Now, what makes a series be a geometric series is as we go from one term to the next, there is a common ratio. Now, what that means is we multiply the previous term to get to the next term. So a good example of that would be like 1 and then 1/3 and then 1/9 and then 1/27. Hopefully you could see in that example what is happening is to get from the first term to the second term, I just multiplied by 1/3. To get from the second term to the third term, 1/3. It's always 1/3 in this case. And that's not obviously the only ratio, but that's the one that in the example that I used. And that pattern would continue on forever. The way that we tell whether or not a geometric series is convergent is pretty simple. We just look at that common ratio, and if that ratio is less than 1, then we know that our series is going to be convergent. Furthermore, and this is kind of nice, but furthermore, of all of the series, geometric series are the only series that we can actually find the sum for. Remember, that sum is always the first term in our series that we are looking at, divided by 1 minus whatever that common ratio is to get from one term to the next. That is how we tell what a geometric series adds up to. It really is the only series that we can know immediately if the ratio is less than 1 what it's going to add up to. All the other ones we can tell whether they're convergent or divergent, but that doesn't necessarily mean that we can tell what they are going to add up to. The next series we're going to talk about is a p-series. Now, a p-series is a series that it has to be written in a specific way. It's just our general term is going to be 1 over n to the p power. So we're going to have a summation, n equals 1 to infinity. And really, this can be, so n is any number greater than 1, which makes sense because I'm going to be plugging in 1, then 2, then 3, then 4, on and on and on. And p is the power that it's being raised to. So if I've got 1 over n to the p, I am good to go in my series. Although I have to know what p is. The way that we tell whether a p series is convergent is we simply look at the power that n is being raised to. If it's greater than 1, it's convergent. If it's less than or equal to 1, then it's divergent. One of interest that we've talked about a whole bunch of times is the infinite series of 1 divided by n. This is what is known as the harmonic series, and it's kind of interesting because you look at it initially and you might say, oh, it looks to me like that is a convergent series, but in reality that is divergent, and that gets used an awful lot when we look at that particular series. An alternating series is a series that alternates between positive and negative terms. The way that we can tell that we're looking at an alternating series, that says negative, it's supposed to say alternating. The way we can tell if we're looking at an alternating series is because the general term usually has either a negative number being raised to a power or negative 1 being raised to the nth power. When we notice that we have an alternating series, the way that we tell whether an alternating series is convergent or divergent is we basically see if we get rid of the negative portion of the alternating series, are the terms getting smaller and smaller and smaller. And the easiest way to do this is, again, get rid of the negative part and then plug infinity in for n. If you get 0 when you do that, then what is happening is the series is getting smaller. It doesn't have to be getting smaller fast enough. It just has to be getting smaller, and you can tell whether an alternating series is convergent just by looking at that. Okay? As a quick side note, when we talked about alternating series, one thing that we discussed as well is what it means to be conditionally convergent. Okay? When we look at something that is conditionally convergent, what we're basically saying is, okay, I've got a series here, and it's an alternating series. But in order for that series to be convergent, I have to have the alternating part. So in this case, I know that this is the alternating harmonic series. Okay, it goes negative 1, positive 1/2, negative 1/3, positive 1/4. And I can see that my terms, if I ignore the negative and positive, are getting smaller and smaller, so that I can tell that that series is convergent, which is what I need for an alternating series. But the only reason that's happening is because I have the negative 1 to the nth power on top. This series is convergent, but unfortunately, if I got rid of the negative, it would no longer be convergent because it would just turn into the regular harmonic series and it would be divergent. When that happens, where you have to have the alternating portion of the series in order to be convergent, we say that it's conditionally convergent. If I can get rid of the alternating thing, then we say that we call that absolutely convergent, which means that I don't need the negative to make it be convergent still. Okay, so again, the alternating harmonic series would not be. It would not be. So here's a couple of tests we can use. Once we have a series and we think we know whether it's convergent or divergent, we can use something like the direct comparison test. Okay, the direct comparison test is a test that we use when we know that a particular series is going to give us terms that are going to be smaller no matter what than another series that is convergent. And that's usually a P series. Okay, so the way the direct comparison tests work, and here's just an example, I have a series where I've got 1 over n squared plus 2, and I know, because this is a P series where that power is bigger than 1, I know that this series is convergent. Well, by looking at the terms in this series, this new one, 1 over n squared plus 2, I know that all of those terms are going to be smaller than the terms that are in 1 divided by n squared. And if all of the terms in this add up to something, then since these terms are smaller, I know that that one is going to be convergent as well. Now, the reason why I know that those terms are smaller is because I'm only adding something to the bottom of that particular fraction. If I'm subtracting something, so I don't know for a fact that that's what's happening, what we use instead is the limit comparison test. The only difference between the two, honestly, is the limit comparison test, we think this series is going to converge, but we don't know for a fact that every single term is going to be smaller than the term before it. So here's how the limit comparison test works. You take a series that, here's just a real quick one. Let's say I had n equals 1 to infinity. I'm just going to go with very similar to what I had last time. N squared minus 2. Then I've got n equals 1 to, let's make this 3 right here. N equals 3 to infinity of 1 over n squared. Now those look very similar, and quite honestly, you can probably look at this one we know is convergent already. You can probably look at this and know that it is convergent as well, but because I'm subtracting 2 every time, I don't know for a fact, since I'm subtracting 2 on the bottom, that every term in this new series are all smaller than this one. So what we use instead is we use the limit comparison test. All we do on the limit comparison test, and it doesn't matter which order you do it in, you just make a limit of the general term. You take the limit as n approaches infinity of the general term divided by both of them. And it doesn't matter which order you put it, top or bottom. If you get any number bigger than 0, then that means that they both do the same thing. In other words, if I got, in this case, I would get 1 if I was to make that limit. I would get 1. That means that since this one is convergent, 1 over n squared, I would know that 1 over n squared minus 2 is also convergent. Honestly, in most of these problems, you can just look at the problem right away and tell whether it's convergent or divergent, but that's what the limit comparison test is. Now, the ratio test is basically a test where we're comparing 2 consecutive large terms in our series, and I mean very, very large terms, to see if the series is converging quickly enough to 0. The way that we use the ratio test, and I know it looks really long, is we do this right here. And as you're aware, we do use the ratio test when we are looking at Taylor series to determine intervals of convergence, but that's not what we're talking about right here. Instead, we just do the limit as n approaches infinity of 2 consecutive terms that are very, very large in your series, where the normal term is on the bottom, then the term right after that is on the top. When we do that limit, we always get a number, okay? If that number is less than 1, then we can say that the series is going to be convergent. If that number is greater than 1, then that series we automatically know is going to be divergent. And if we get that that number is equal to 1, then we have to use a different test. And we usually use the integral test to do that. Not always, but that's usually the test that you end up using. So that is what the ratio test is used for. Okay, and we've talked about that a lot, and we'll go over some examples in a second. So the integral test is a test that we can use if our series looks an awful lot like a function that is continuous, positive, and decreasing. The way that we use the integral test is we compare a series and a function that take on very similar characteristics, like x squared and n squared, or 1 over x squared and 1 over n squared. So what we do is we see if that series is the function is continuous, positive, and decreasing, then we make ourselves an improper integral, like this one we've got from 2 to infinity of 1 over x squared, and we compare that to the infinite series. What that's saying is if I can actually find out what this is and figure out whether this is convergent, that means that this as well has to be convergent for a lot of reasons that they get kind of complicated. So anyway, that is how the integral test works. It doesn't show up a ton on the AP test, but if you see the phrase continuous, positive, and decreasing about a function, you can almost guarantee yourself you're going to be using the integral test. So what I want to do real quick now is just look at a couple of examples. If you're watching this video for the first time and following the guided notes, I would actually tell you to try the problems first. Pause it here, try the problems first, and then look at how I do them. So the first problem says, what is the value of negative 3 to the n plus 1 over 5 to the n? Well, notice that it is asking what is the value. Anytime it's asking what is the value of an infinite series, we know automatically that that is going to be a geometric series. A geometric series, I need the first term, so I take 1 and I plug it in. 1 plus 1 is 2. Negative 3 squared is 9. Divided by 5 to the first power, that's 9/5, over 1 minus, and then I need to subtract off the common ratio. Well, the common ratio in this problem, it's always whatever's being raised to the nth or n plus 1 power on the top and the bottom. So in this case, I've got negative 3/5 is my common ratio. Now at this point, we just need to do some math. So I've got 9/5 over 1 plus 3/5. So that is 9/5 divided by 8/5. Which gives me 9 over 8. That is what that series is going to add up to. Again, it's geometric. Let's take a look at another geometric one. What is the sum of this series? Okay. Again, I need my first term, so I've got negative 2 to the first power over e squared. 1 plus 1 is 2. That's my first term. over 1 minus my common ratio is whatever's being raised to the nth or n plus 1 power on the top and bottom. I get negative 2 over e. So I've got negative 2 over e squared. Here, I'm going to have to get a common denominator. So I'm going to have e plus 2 divided by e, because 1 is e over e, and then two negatives make a positive. Well, now I've got a fraction divided by a fraction, so I've got negative 2 over e squared multiplied by e over e plus 2. That e crosses out with one of those. I've got negative 2 on top. I distribute the e on the bottom, so I've got e squared plus 2e. And so my answer here is letter B. Now, one thing, this does say the series diverges. You do have to check to see if the common ratio without the negative is less than 1. E is bigger than negative 2, so I know that that series converges. Okay? The next one, which of the following series converge? Well, I look at the first one, and I see that it's an alternating series, but even though it's an alternating series, I look at it, I'm like, oh, it's going between negative 1 and positive 1. That's not adding up to anything in particular. So although it doesn't go off to infinity, it never adds up to a specific number. It always flops between 1 and 0, depending on how many terms we're talking about adding up. So that series does not converge. 1 plus 1/3 plus 1/5. And again, I always just like to look at the general term to see what's going on. Notice that that is very similar to the harmonic series. Since the harmonic series is divergent, technically what we would use here is we would use the limit comparison test, because that is a -1 on the bottom. But hopefully you can see real quick that that series is also divergent. The last one is a geometric series, because from one term to the next, we're getting bigger by 1/3, so that's geometric. That is less than 1, my ratio. So I can see that 3 is our only convergent series there. Which of these series converge? Well, I look at the first one. I'm going to change that real quick. I look at the first one. Anytime we see sine, we know that that value is going to go between 1 and negative 1. So at most, that's going to be 1. 1 over n squared, that's a p series. I know that that one is convergent. The next one, I've got 1 over e to the n. Okay, well, n is going to be getting bigger and bigger. So that is also going to be convergent. That's actually a geometric series is what we're looking at there, where each term gets bigger by 1 over e. Number 3, we would actually have to use probably, honestly, the limit comparison test. We might be able to use direct comparison, but limit comparison, really all you have to do is look at the highest powers on top and bottom and then make a fraction out of it. Oh, we have ourselves a harmonic series. That is not convergent, so 1 and 2 are our answers here. This one, which of the following statements are true about this series, where it gives us the general term? Well, I can see that it's alternating, so I know 1 is true. I can also see, now I've got the limit as n approaches 0, or as n approaches infinity is 0. Well, the negative 1 isn't going to do much. When I plug infinity in, what I really have is like 1 over the square root of infinity there. So honestly, that is 0 as well, so that's also going to be true. And once n gets bigger than 2, the terms are going to get smaller and smaller, and that's all this is really saying here. So 1, 2, and 3 are all true about that series. Lastly, okay, if I had, they loved these ones on the AP exam. If I got a problem like this, it says I've got B is less than A for any term greater than 1. This says if n, the limit as n approaches infinity of A sub n is equal to 0, then B sub n converges. Well, you think about it at first, you're like, well, if all the B terms are smaller than the A terms, and this is saying that the terms get smaller and they get to 0, that might be true. But again, I think of the harmonic series, okay? That series is not convergent, but this statement is true about that. So that doesn't mean that B is going to be true, A is out. Letter B, if the summation from 1 to infinity of A sub n converges, then the limit as n approaches infinity of B sub n is equal to 0. Well, that is actually the true statement here, because if this converges, that means my terms have to be getting smaller and smaller and smaller, and all of the terms in A are going to be larger than those in B. That's what that first statement says. So letter B is true on this one. C, just because B diverges doesn't mean that A has to necessarily, because A is greater than B. Well, that one doesn't, hold on just a second. If B diverges, then that automatically means that the terms are not going to 0. And even if they are, it'd be a harmonic series. That's impossible. Okay, so if A diverges, B diverges, that one's not true because B is smaller than A, so it's entirely possible that one does and one doesn't. And if B converges, A doesn't have to be converged because those terms are larger. Okay, so our answer is here is B. Now, hopefully all of that kind of made sense. I know that was a little bit longer, but that covers everything that you need to know for series. They show up on the multiple choice portion of the test often, so hopefully that made sense. If you have any questions about that, please let me know.